All right, so let's pick up right where we left off. So this is 4.11b, okay? And I want to give you an example like this. So this is actually the same RF and K that we had on the previous video. And I want to ask you, which of these family of reflexivity relations does R have? Which of this family of reflexivity relations does F have? And which of this family of reflexivity relations does K have? Pause now. Okay, hopefully you've had a chance to pause and do pause and think this through for yourself, okay? So what you're seeing here is an example in R of a reflexive relation. Everything in the domain bears R to itself. A does, B does, and C does, okay? Now, let's go ahead and take a look at the relation F. So A bears the relation to itself, B does not, and C does. So some things in the domain bear R to themselves and some things do not. Therefore, F is an example of a non-reflexive relation. Okay? Looking at K, A doesn't bear it to itself, B does not bear K to itself, and C does not bear K to itself. So that would be an example of an irreflexive relation. K is irreflexive. All right? So that's basically what can go on there, and I want to re-emphasize the point again that on the empty domain, the relation is both reflexive and irreflexive, but that's the only time that can happen, okay? Okay, now what I want to show you is that in addition to reflexivity, there are two other important families of relations: the symmetry or the symmetric relations and transitivity or the transitive relations. Let's start with symmetry, okay? Symmetry spelled this way. Okay, symmetry. All right, so what we're going to have is a very, very similar setup here where you're going to have three relations that exhaust the different logical possibilities. Okay, so what we're going to do here is we're going to define a relation R is symmetric if and only if that. And then here, instead of irreflexive, we're going to have asymmetric, okay? And so this is all going to exhibit the same pattern as the reflexivity case, and that's what I'm trying to point out here. And then you're going to have the case where sometimes it's symmetric and sometimes it's not symmetric. At least one case it is, and at least one case it's not. So non-symmetric, okay? So it's all going to go in this very patterned way, and I hope that that's making this clear to you. So what we're going to do now is actually define the relation of symmetry, which is a little bit more complex. Let's give ourselves a little bit of space here. So like this, symmetry or a relation is symmetric if and only if it satisfies this description. So it's going to be if Rxy, okay, then it's the case that Ryx. So if the first thing bears it to the second thing, then the second thing bears it to the first thing. Okay? Similarly, we're going to basically define this this way for asymmetry. Okay? For asymmetry, is if the first thing bears R to the second thing, then the second thing does not bear R to the first thing. We're going to do plenty of examples shortly. Okay? Just let me get the definitions on the board. And then, of course, we're going to have this case. So let's do this. And we're going to need a second quantifier here. Like that, okay? So in at least one case, the relation behaves symmetrically, and in at least one case, the relation behaves asymmetrically, okay? So these are the formal definitions of these, all right? Let's go to our visualization so we can see if we can figure out what's going on with these formal definitions. Okay, so let's start by thinking about the symmetric relations, okay? And they're defined this way, where this is our arrow, okay? So for everything in our domain, which has three objects, it's got to satisfy this description, okay? So let's think about a couple of different cases together here. Let's suppose, for example, that A bears the relation R to B. If R is in fact a symmetric relation, what must occur now? Pause. Okay, what must occur now is that B bears R to A. Okay, if they're going to be symmetric, then it's got to satisfy this description. Okay, it's kind of an interesting thing. All right, now notice in this particular situation, we do not have B bearing R to C, and we don't have C bearing R to B, and that's okay. This would still hold as R being a symmetric relation because it just requires that if, you know, one of the things bears R to one of the things, then it has to bear it in the opposite direction. Now notice this, right? If the object C here has the relation R being born to itself, okay, that would automatically satisfy the question of symmetry, because the idea is if R XY, in this case RCC, then RCC, and so that would automatically satisfy the definition of symmetry. So if we imagined a domain that had one object in it, just one, not three, one, and that object had R being born to itself, then that relation would be symmetric on that domain, okay? And similarly, if you had a one object domain and it didn't have R being born to itself, that would also be, hold on a second, sorry about that, that would also be symmetric, okay? Because again, in order for it to not be symmetric, you would have to have at least one thing that for which this failed, okay? So let's talk about what that would mean. What would it mean for you to have a case of a relation that was not symmetric? Well, let's just suppose you had A being bearing R to B and B not bearing R back to A. Then, you know, this holds and this fails. And therefore, that would not be a symmetric relation on that particular domain, okay? That's exactly what it would look like. Okay, one last problem here. Let's suppose that we've got a symmetric relation, okay, and let's suppose that B bears R to C, okay. In that event, what must occur if R is in fact reflexive? Obviously, we're pretending this is not here. Okay, so if B bears R to C and R is in fact symmetric, then C is going to bear R to B, okay? And that's what symmetry is all about. All right, let's talk about asymmetry. Okay, so a relation R is asymmetric provided it satisfies this description. So let's go through maybe a couple of cases together. So let's suppose that R is in fact an asymmetric relation, and let's suppose that C bears R to B, okay? What must be required now given that R is an asymmetric relation? Okay, hopefully you've had a chance to think on that. But if R is in fact asymmetric, then it's got to be the case that B does not bear R to C, okay? And similarly, let's suppose that on top of that, C bore R to A. What must be required if R is in fact an asymmetric relation? Well, it's got to be the case that A does not bear R to C, okay? So that's basically what we've got going on here, all right? And that's what asymmetry requires. Now, let's talk about a couple of other special cases. First of all, let's consider the case where nothing bears R to anything, so everything has sort of got a slash through it, okay? What happens then, all right? Well, in that event, what's going on? Pause now and think about it. Is that relation asymmetric or not? Okay, that relation is in fact asymmetric. It is, right? It satisfies this test, right? Nothing satisfies this, right? And so the antecedent is always false, and therefore the conditional is always true, and therefore this is satisfied. So that would turn out to be an asymmetric relation. So again, that's like a special sort of case to think about, and I want to make that explicit. Okay, let's talk about another special case. Suppose we've got an empty domain. Is that relation asymmetric? Okay, on the empty domain, that absolutely is asymmetric, right? Because, you know, this is true on the empty domain, right? Everything satisfies this description. You know, there's no counterexample, okay? So those empty domains are special. By the way, on the empty domain, the relation is also symmetric. Okay, that's the only time both of these can hold. Otherwise, once again, they're mutually exclusive and mutually exhaustive categories. Okay, so that's what you got to think about. Now, what would be a good case where the relation is not asymmetric? Can you think of a situation defined on a domain with A, B, and C where it's not asymmetric? Pause now. Okay, so any case where it behaved symmetrically. So if A bears R to C and C bears R to A as opposed to not, that would be a case, because then this would not be satisfied, right? If A bears R to C, right, and it's asymmetric, then C cannot bear R to A. So imagine a case where A bears R to C and C bears R to A. That would be not asymmetric, okay? All right, let's think about the case of non-symmetry and what that looks like. Okay, so the non-symmetric case is defined this way. We need at least one case where the relation behaves symmetrically, and we need at least one case where the relation behaves asymmetrically. So perhaps the easiest illustration of this, diagrammatically would be, like this. So here's a case where it's behaving symmetrically, and here's a case where it is behaving asymmetrically. Okay, and therefore, taken as a whole, right, this would be an example of a relation on a domain that is non-symmetric. So sometimes it's behaving symmetrically, sometimes it's behaving asymmetrically. Therefore, it's just non-symmetric. It's not completely symmetric, and it's not completely asymmetric. Okay, and that exhausts all the logical possibilities. Okay, let's try a couple of examples on our other screen. Okay, so let's start by trying to do some examples in ordinary English of relations which satisfy and don't satisfy these properties. So let's start with symmetry, okay, with a relation being symmetric. Can you think of a relation in ordinary English like is greater than or something like that? It's an ordinary ho-hum relation that you're familiar with, which is in fact a symmetric relation. And can you also provide me with an example in ordinary English of a ordinary ho-hum relation which is not symmetric, which is not this way? Pause now. Okay, so we'll just do our handy example of is the same color as, right? Notice that is in fact a symmetric relation, right? If you've got 10 objects in your domain and they're all, colors, right? Then, if this thing is the same color as this thing, then this thing is the same color as that thing, right? And so that would be an example of a symmetric relation. Can you think of an example of a relation which is not symmetric? Sure, is taller than. Let's just take that as an ordinary relation, right? So notice that if x is taller than y, it does not follow that y is taller than x, and therefore is taller than is not a symmetric relation, does not have this formal property, okay? Go ahead and try asymmetry right now. Can you give an example of an asymmetric relation, an example of a relation which is not asymmetric? Okay, I hope you've had a chance to think about it, but let's take, is greater than as an example, right? Is greater than is absolutely an asymmetric relation. Notice, if x is greater than y, then it's not the case that y is greater than x. Right? And so greater than is an example of an asymmetric relation. It has this formal property. Kind of nifty, right? And so now you're hopefully starting to see like why these things are so historically important. An example of a relation which is not asymmetric, let's say, is identical with. It's a relation we're going to study in the next two sections intensively, but notice that if A is identical with B, then it's not the case that B is identical with A. No, that fails. So this would not hold for this particular relation, and therefore this particular relation is not asymmetric. Okay, let's spill on to the next video while we'll finish this and do some more examples of these together. So look for video 4.11c.